so.
Hey,
So I am biased. Oops, gotta chat. Let's see if someone's gonna talk. Right sider's ready to eat. Yeah. All right. So I want to talk about some applications today of what we've been discussing, and halfway, I got a short thing I want to continue on gas phase reactions in Lindemann Hinchelwood. And then I'm going to transition into a different topic, which we're going to cover over, we'll return to after the break, which is on catalysis. So we'll start talking about catalysis today as well. I want to just extend our unimolecular theory of collisional deactivation, second order low pressure, all this junk we talked about. I want to extend it, and I want to claim that this is a universal process. And so I want to look at a reaction in particular where, in some sense, the kinetics should be instantaneous. We shouldn't even have to think about it, but still we have to consider the pressure, and the kinetics are dependent on the pressure. So I want to look at some reactions that are barrierless, right? Barrierless reactions. And I'm just going to look at one example and then give you another thing to think about, but I won't go into too much detail. Right, but a reaction where the activation energy is 0 or less. Right, and so if that's the case, right, Arrhenius tells us that the rate constant is A e to the minus delta, E sub A. Let me erase that. Sorry. Over RT, but EA's barrierless reaction, EA is 0. So the rate constant, at least at Arrhenius's level, is just a number. It may have some temperature or pressure dependence. We're going to consider that, right? So it's just A, right? So there's no temperature dependence, at least at first order. It's kind of our first approximation. It's just a number. And I want to see how true that is. So we'll look at an example that will assess this, that Kr is just the constant. But we should ask the question, is A truly just a number? Or is it a function of some parameters? I should say rather the function of the experimental conditions, right? Does it have some temperature and pressure dependence, for instance? Change, right? This would imply that no matter what condition we run it at, it will give us the same rate. Rate is flat. Right, so let's look at an example of barriers reactions. And there are entire classes of reactions that have no barrier, but they come from reactions of molecules that, of course, my class starts my mic cold, as usual. Been doing that for like last 3 weeks. Good time. He's probably trolling me at this point. So I lost my track. There's a whole class of reactions of a specific class of molecules. We'll look at 2 classes in particular, where there is no barrier when they recombine. And the one I want to look at and focus is I want to focus on reactions between radicals, free radicals. Radical reactions are, as far as I remember, I can't think of any that aren't barrierless. And so the general scheme is that you have 2 molecules of unpaired electrons. You have A with an unpaired electron and B with an unpaired electron, and they collide to form AB. Okay, this should hopefully make sense why it doesn't have barrier, right? We know that electrons want to be paired. Right, so there's a very, very strong impetus for the electrons to pair together. And of course, you could also say, well, there's probably some competition here from A reacting with A itself to form an AA and B reacting with B to form B. Let's not worry about that too much. But the idea is that you have 2 species that have unpaired electrons. All they want to do is put those electrons together. There's a huge energetic stabilization coming from pairing those electrons. And it's not too hard to think that if you bring an unpaired electron here, an A and an unpaired electron B here, and they start to come together, there isn't at long distance, right? Remember that we saw that things that have the same charge at long distance attract each other. So as they start to approach, there's no repulsion. And now you would say, okay, well, A and B start to get closer and closer together. Now you've got this one unpaired electron here and this one unpaired electron here. You get these two negative charges and they're getting closer. They should repel. So you would think, okay, maybe there is a barrier here. Because the electrons, these two unpaired electrons get so close to each other that they repel each other. But in fact, that's not the case. Because there's a special property of electrons that negates that. So, and it's one of those things that's quite special about chemistry, is that the electron repulsion between radicals is negligible. And there's a good reason for that. Electrons have a charge, -1, but they also have another property called spin. Electrons have what we call a spin angular momentum. It's in some sense we call them up electrons and down electrons, right? You remember when you do those electron configurations in Gen Chem, you pair an up electron with a down one, up arrow, down arrow. These correspond to this spin property of the electrons. And we're not ready to talk about spin. Of course, we're going to talk about plotting next semester. In fact, one of our first lectures in next semester is on spin. It's a very important property. But the thing is that this is negligible because electrons can orient in opposite spins. Right? So you have kind of like an A atom here. It's got this unpaired electron orbiting it. And we could just say that it's spin up. And then we bring in B. And that electron is spin down. And now I have electrons of opposite spin. And what you can show, and again, we're getting into microscopic chemistry. It's not really the point of this class, but we should think about this a little bit because it's important. When you have a spin up and a spin down electron that are unpaired like this and they're nearby, they don't repel each other. In fact, they want to come together, right? There's some there's some stabilization coming from pairing. So even if there is some repulsion between them, it doesn't matter. The attraction between them is much greater. But what I can say here is that the stabilization due to pairing the spins or matching them dramatically outweighs any sort of repulsion. So the idea is that thermochemically, energetically rather, or however you want to call it, when A and B come together, they just are attracted to each other. The energy just goes downhill. Right? So this has no barrier. So let's look at an example. Of two radicals that react, and this is a well-studied reaction in chemistry. Take oxygen atom in the gas phase, and NO, which is also a radical. This is one of the few nitrous oxide. You can buy tanks of this. This is laughing gas. So maybe some of you have even enjoyed the presence of this radical. But when it reacts with oxygen atoms in particular, this reacts rapidly to form NO2. The two electrons pair. NO2 is a nasty, nasty gas. This is brown. This is a brown gas and it's toxic. This is a downhill reaction, completely barrierless. Okay, so let's look at it. Let's just convince ourselves that in fact the thermochemistry is exothermic. So we can go look this up at an ATCT. We can calculate the enthalpies of formation of our three molecules. At room temperature, kilojoules per mole. All right, now oxygen, of course, its standard state is O2. So oxygen was going to have a positive enthalpy of formation because you have to break the O2 bond to form O. So it's at a higher energy state than its natural precursor O2. And it's at plus 246.8 kilojoules per mole. Right? And again, what this tells you is, again, a nice thing to think about. The enthalpy of formation of O is 246. And the way that we construct that number is by calculating how much energy it takes to break O2, which has enthalpy 0. What it says is that oxygen has 246. You get 2 oxygen atoms from breaking O2, cutting it down the middle, 2 atoms. That means that OO bond is about 500 kilojoules. Right? It takes about 500 kilojoules to break an OO bond. And as someone with experience with what we call cracking O oxygen, people, when you convert oxygen O2 gas into oxygen atoms, we call that cracking the oxygen. It doesn't happen until at 1 bar until about 1500 Celsius. It takes a lot of heat to break O. But you can make O atoms. They're present in the atmosphere. They're present at high temperature. They're present at low pressure. There's lots of places where O appears. This is a common reaction in the atmosphere, for instance. NO is a little more stable. And NO2, which has no radical. Sorry, that's no radical. Let me just erase that. A fully paired molecule. It has this enthalpy of formation of about 36.87. All right, so my significant digits are terrible here. Forgive me. But we can immediately see that this reaction is downhill because the enthalpy of reaction is the products 37 minus the sum of the reactants, which is 246 plus 90, 350 here. So the total enthalpy of this reaction is about 36 minus 330, give or take. And so this reaction is extremely exothermic, as we would expect. About 300 kilojoules per mole, it loses energy. All right, so this reaction, if we're about to draw a coordinate, it starts at, say, 0 energy and then loses 300 kilojoules per mole of energy as it reacts with no barrier. It's just a downhill slope of energy. Let's go ahead and plot that. We'll put energy here, and this is our coordinate. Put the products here, NO2. Here's our reactants, O plus NO. I'll set my energy for my O plus NO to be at some number 0, just a relative number. You don't have to do that. We should say this is delta E rather. And our NO2 is at minus 300. Way down in energy. So much down in energy, I should just break my scale a little bit. This reaction just takes this state and then just goes straightly down in energy like this. This energy difference is minus 300 kilojoules per mole at 298 Kelvin. So at standard temperature, it's about 300 kilojoules per mole. Right, barrierless reaction. Right, so you imagine now bringing O together and an NO together, and they should just react immediately. Not so simple. Let's think a little bit about the mechanism. What steps need to go? But again, you would say, okay, well, O and NO come together and then NO2 forms, and that's it. Right, but we have to deal with conservation of energy here. Right, because what happens is that when the O and the NO, they come together at zero energy, right, relative energy. Okay, so immediately when the complex forms, when the O and the NO are right next to each other, right, they first combine, they're still at 0 Kelvin, or sorry, 0 kilojoules. They haven't lost any energy. The energy is conserved. And so there's some complex that's at high energy. The product should be minus 300. But when they come together, they're initially at 0. So there has to be some sort of energy loss, right? We have to take this process, which they come together at 0 Kelvin, and then drop down into the well, into the final product. So you have to get rid of 300 kilojoules per mole of energy in this reaction. Right? Well, if this is in high pressure, right, we can have tons of collisions. But what if we're at low pressure? What if we're in the atmosphere? It's not so simple. So what we should do is think about this from the Lindemann-Henschel perspective. Right? So we're going to think now what we're going to have is NO plus O. And it's going to react to form some excited state of our product. Something like that. Some excited state. What's the energy of this excited state? Well, the energy of the products is 0. And therefore, the excited state should be 0. They just come together. And then you eventually form your NO2 product at minus 300. So we have to find some way to kick this energy out, right? That's a lot of energy. Right? Remember, because of microscopic reversibility, anything is possible to go backwards that can go forwards. Right? So if it's really easy for NO and O to go to this point, it's just as easy and likely that this goes back. Right? The equilibrium constant here is 1. So if I were to write a KEQ for this, we would basically say it's 1. Right? So it's equally likely to be on either side. Right? So the reaction, right? So we need some process that's going to kick this out of energy yet. It's really hard to pull out 300 kilojoules per mole of energy, right? That's almost an entire bond's worth of energy. And so this system is just going to bounce back and forth. So we have to find some way to pull it out, right? So what we need to introduce is a collision partner. Right? There needs to be something to soak that energy up. So what we can do is add an atom M, where M is just some collision partner. It could be an air molecule, a nitrogen, a helium, whatever you want. And it's going to soak that energy up and pull it from the excited state at NO and then transfer that energy inelastically to the atom. Right? So M is some collision partner. We need to bath gas, as we call it. Right? It's something that it can smack into but not react with. The typical M's in experiment are N2 is a good one, helium, argon. Those are some common choices. Atoms that are more than happy to smack into something and take some energy, but don't react. Right. So what in reality, so at low pressure or at any pressure, this reaction requires a collision. So let's go ahead and put that kind of scheme on our reaction coordinate. We have this excited state now. Which is our partially formed NO2. You can think of this NO as being like a Voltron is taking in this other oxygen, hasn't quite put the arm on, like a Gundam or something like that. It's half there, right? But you got to get all that energy out to lock it into place. And so there's going to be some rate, right? Some collisional rate or some rate of association. That brings us here. Right, which is in some sense the rate of collision of O and NO. And then there's another rate that brings us down to the final reaction, K2, K minus 2, which is mediated by a collision with our excited state atom. So we have plus M here, and then down here we have plus M. Some excitement here. So I won't go through the math here, but the math works exactly the same as it did for Lindemann Hensel would. We're going to write the total rate of formation of our products and take this NO intermediate as a steady state material. It would be our short-lived intermediate. The concentration is basically the concentration's time derivative is 0, meaning that the concentration is constant, right? So we apply Lindemann Hensel would. Right, where we treat our excited state complex with 0. And again, just like before, you get a low pressure and a high pressure limit. So at low pressure, you find that the rate of formation of NO2, our product, is equal to K2 times the concentrations of our reactants, as it should be, times the concentration of our bath gas. Right? So the important thing here is that the rate is determined by the collision rate. And it also depends on the bath gas concentration, the total pressure of the system. So this is linearly dependent on the total pressure. And if we double the pressure of helium, then the reaction goes twice as fast. Right? And then at high pressure, right, those collisions are happening all the time. And we lose that ability. It's proportionally equal to, there's some slight differences, but it's mostly proportional to the rate of which NO and O see each other. Right? And that's what we would expect for this reaction, right? We have two objects that have no barrier. All they need to do at high pressure, right, which assuming they can constantly collide and remove energy, all they need to do is just come together, right? So we get second order kinetics, first order in both of them. Double the amount of NO, reaction goes twice as fast. But at low pressure, we have to depend on the total pressure of the system, which includes our collision material. And so again, the conclusion is just like what we had before, that even in bimolecular reactions, right, this is a bimolecular reaction. The kinetics necessitate, right, they require a third colliding body. Interesting. Well, even reactions, right? In fact, depending on who you ask, if you ask an organic chemist how stable are radicals, they'd say they're not stable at all. Right? So they just disappear immediately. And that would make good sense to an organic chemist because typically they're working at high pressure. They're working in liquids. They're working, at a bar. And so these kinetics take over, and NO and O are always going to find each other. It's not hard for them to find each other, and so they tend to react very quickly in the world of organic chemistry. They're just short-lived species. But if you were to ask a gas phase chemist how long these are how stable these are, well, they'll tell you, well, it depends on the pressure and depends on the temperature. Because if you can create a process or an environment where NO and O react fairly slowly. And the way you do that is you just minimize the pressure. Another thing to think about as well is that this is an exothermic process. Well, let's think a little bit about the Gibbs free energy of this reaction. Right? So first of all, delta H is very, very negative. But what about S? What about the entropy of this system? Well, the entropy is actually ordinary. Entropy change is a negative change. And the reason why is because these are just gas atoms, so we can just treat them as ideal gases. We have 2 moles of ideal gas in the reactants, with 1 mole of ideal gas in the products. Delta S has to be less than 0 here. Going from 2 moles to 1 mole. The entropy drops by effectively a half. So the entropy is decreasing, right? So, and Gibbs free energy, which is H minus TS, you have a negative H, and then your TS has a positive contribution. So what this means is that as temperature increases, the Gibbs energy shifts towards the reactants. So start with a negative number at 0 Kelvin, minus 300. Subtract off TS. S is negative, so you add TS. And so the Gibbs free energy becomes less negative as T increases. So what that tells me is that if I want to do this, if I want O and NO to be stable, I have 2 options. One is that I can run them at low pressure. That's certainly going to work extremely well because the rate of formation is dependent on the concentration or the pressure. But if I crank the temperature up as well, that actually slows the reaction down. Now, why is that? You would think that would be the opposite, right? And typically, we think materials should react faster at high temperature, right? They tend to be less stable at high temperature. But this reaction is the opposite. Because what happens when you increase the temperature? Well, your reactants, there's 2 moles of gas, and your products are 1 mole of gas. So let's think a little bit about the heat capacities. As temperature increases, the heat capacity of the reactants increases twice as fast as it does for the products. Because there's 2 moles instead of 1. They all have roughly the same heat capacity. They're all ideal gases. We're treating them as like nothing different between them. So this has some heat capacity. This has some heat capacity. This has some heat capacity. So you have 2 heat capacities over here adding together and 1 here. So as temperature increases, this point goes up in energy. And this side goes up twice as slow, half as fast. So as temperature increases, the enthalpy of reaction gets larger. It gets more exothermic. So as T increases, delta H gets more negative. And therefore, when M comes in to pull that energy, it now has to pull more energy out in that collision. Right? It's even harder to extract that energy because now you have to extract, say, 400 kilojoules per mole instead of 300 kilojoules. So this reaction becomes even less effective at high temperature. So the way that we would want to stably store these radicals is at high temperature and low pressure, right? It's completely contrary to what you would imagine. It turns out that radical reactions are really, really, really effective at low temperature for this reason. The enthalpy of reaction is minimum. So that means the collisions there's a much smaller threshold for an effective collision at low temperature than there is at high temperature. So in space, for instance, radical recombinations are a dime a dozen. They're much less frequent at high temperature for this reason. There's not enough energy there's just too much energy to pull out. It's kind of a little contrary to what you would expect. Okay, so the important thing here is that the rate of NO2 formation is proportional to the pressure. So I just have one more plot to show you. We can look at experimental data. or O plus NO, NO2. And just to save me some time, I'm just going to copy what I drew last class. So let's look a little bit at this plot. This is a plot of the pressure of the reaction, of the concentration of NO, the number of moles because it's a constant volume, times and versus the observed rate. Remember at low pressure, that the rate of formation of NO2 ET is proportional to the collision rate of M with NO, so that's K2 times the concentration of M times the concentration of O times NO2 or NO. All right, so this is low pressure. And high pressure is K1, the association rate of the two radicals, times O and O. Right? So if I underline the things that are in common with each other, at low pressure, there's this additional factor of collision partners. The rate is dependent on this K2 value, the collision rate, times the concentration of the collision partner. And here it's just a number times the concentration of NO. If we do this reaction pure, right? This was done pure. So M here is just the molecules themselves, right? Just the molecules themselves. Then at low pressure, we could say, well, let's say we have NO in excess, all right? So it's just NO. This is an excess. All right, so the majority of the molecules in there are NO at low P. This means that the rate of formation of NO2 dt is equal to K2 times the square of the NO concentration times O. So if it just has to collide with itself, now it's second order in NO. All right, so let's look, and then at high pressure, it's just first order in NO. I'll just put a 1 there just to drive that home, right? So the rate should double. The observed rate should double when I double the concentration at high pressure, but it should go 4x, roughly, at low pressure. And that's exactly what we see here. At high pressure, the rate increases linearly. So the rate of NO2 formation doubles as we double the NO concentration. Great. Well, what happens is there's an or a quadratic roll-off of the rate towards some fixed value. And eventually, as pressure goes to 0, this will eventually go to some fixed value. Actually, it'll go to 0, sorry. But it's a function of the square of NO. All right, so what we see is that in this reaction, right, the kinetics show a discontinuity in the observed rate at some special pressure, right? And again, that pressure for this system just about happens to be 1 millimole. It's purely coincidence it ends at 1, right? At some special pressure, which is where the rate, right? That special pressure is where the rate of collisions begins to become faster than the rate of radical association. That when they come together and say hello. And so you can even see that change as you do a dynamic function of pressure, right? You do your example, you see your rate get faster and faster, but this curve, the scale at which it gets faster changes. And so we would effectively say that this is down here a 3-body reaction, a 3-body process. And at high pressure, it still is 3 bodies, but that third collision is just always there. It just effectively looks like a 2-body process. The 2 bodies come together. And again, this is another reason why radicals are really, really, really long lasting, especially at low pressure and in space. You find tons of radicals in space. OH, for instance, hydroxyl radicals, a dime a dozen in space and in the atmosphere. OH is so abundant in space that it strangely enough, it acts as a laser. It's a microwave, it's called a maser. The absorption and emission lines of OH are so strong that they act like a laser, like a beam. It's really crazy. Maybe I'll show that to the next semester. But OH and OH lasts for a super long time in the atmosphere. You find it everywhere at low pressure, and this is why. Because in order for OH to say form water, you've got to bring an oxygen in, a hydrogen on top. Right? So OH plus H, for instance, would be a really natural way to lose OH and make water. But again, in atmosphere and in space or in the atmosphere, you're in this region. Right? You're at really low pressures. 1 millimole concentration of NO is a lot compared to most places. A lot of pressure. So in real life scenarios, atmospheric and space scenarios, you're way down here. And so they just rarely happen. And so OH and O and all of these radicals, they tend to last a long time on a course of days or years. In space, they last thousands and thousands, even tens of thousands of years. Because it's just so rare for them to meet a third body to react to. Okay. So that is collision, I don't know what you want to call that. Basic gas-phase kinetics. I want to change gears. Right, and I want to look at another kinetic process. What we've been looking at lately has been interactions between reactants and products and thinking about barriers. And most of the things I've been talking about are manipulating the reaction conditions to speed up or slow down a reaction, right? They're in some sense actions on the reactants and the products, right? We're trying to change the equilibrium of the system. But is there something we can do that doesn't change the endpoints of the reaction, but changes the middle? And so we can leave the reactants and the products in the same place. We don't have to change the temperature. We don't have to change the pressure. We don't have to do any of that. But we bring in something into our reaction that takes our activation energy and changes it alone. Something that just manipulates the transition state. And we do have something like that. And the process that we're going to talk about regarding changing transition state is called catalysis. So let's just do a quick definition. A catalyst. What is a catalyst? It's a molecular substrate. It could be a molecule. It could be a surface. So sometimes a molecule. Sometimes it could be a metal surface. Sometimes it's just an atom. For instance, it could just be H plus, a proton, and that would be acid catalysis. Some sort of molecular substrate. That does not contribute to the rate law for the reaction, nor the thermochemistry, right, the delta H's, the delta G's of the reactants and products. Right? But amplifies, accelerates the reaction. That's kind of an awkward way to say that. All right, so let me rephrase that a little bit. All the same things in here. A catalyst is something that that accelerates the kinetics of the reaction, but does not change the products or reactants, the states of the products or reactants, and doesn't show up in the kinetics, doesn't show up in the rate law. So it's just an object that exists in your reaction that participates in the reaction, but doesn't participate in the stoichiometry. Does not appear in the stoichiometry at all. right, so we can just look at a general reaction. A to P. We can just draw a little reaction coordinate. Here's our A to P reaction. Right, it's got some barrier. We can write that barrier as delta G double dagger. And then we apply a catalyst to the reaction. Could be something as simple as we drop it into the flask. It could be that we put it on a surface and run our material over that surface. It could be changing the pH. It could be anything. What happens with the catalyst is that you get the same starting materials and the same products, but the activation energy drops. This is the catalyzed reaction. So we could call this delta G double dagger cat, and this is the catalyzed reaction. That's all a catalyst does. It just participates at the transition state and stabilizes the transition state. It doesn't appear at the beginning, doesn't appear at the end. Let's look at an example. We're going to have a couple of examples today. And then next class, next when we get back from Thanksgiving, I have a whole lecture on a whole example that we'll look at. It's application. Right? So let's look at another example. Let's look at an SM1 reaction. Right, an SN1 reaction. Let's look at ethanol. Sorry, ethyl bromide. Let's look at isopropyl bromide. Right, isopropyl bromide plus OH, some base, to form isopropyl alcohol. Right, we've already looked at a reaction like this, but this is SN1, right? So SN1, remember SN1 undergoes a ionization step where the alkyl halide breaks apart into a cation and an anion. It's a two-step reaction. So let's look at that. Let's say it's downhill, which it should be. So here's our CBr plus OH. I'm just going to write it in shorthand. We have to break that CBr bond. It has some energy. And then we form a stable CH3 2CH plus Br minus. Right? And then the OH comes in to attack, and that's downhill. And we form CH3 2CH OH. We have a little intermediate here. Okay, so we have this little ion pair intermediate here. Right, and there is a barrier to this reaction. Right? There isn't a transition state, but there's a barrier. The reason why there's not a transition state is because, as it turns out, this point right here is not a saddle point. Right? Remember, transition states have to be a saddle point. And so instead of a saddle point, you have a minimum here, which is this ion pair. Okay? So it's an intermediate, a chemical intermediate, not a transition state. But there is a barrier. Right? You still have to break this system apart. You still have to ionize molecules. It still takes some energy. So there's going to be a barrier to this reaction, right? So how do we catalyze this reaction? Right? Well, right. So what would be a way to catalyze this? So we want to bring something in that doesn't change the products of the reactants. Right? So we want to still have the same stoichiometry, but we want to make this process easy. Right? So what we would ideally want to do is choose some material where the barrier is much smaller and maybe even the intermediate is even more stable. And then react something like this. Well, sorry, it has to react to the final product. Sorry. Right, maybe we want something like this instead. Right, so how would we facilitate that? Right, how would we take this and what would we need to add to bring it down here? Well, what we need to identify is what is ultimately making this hard? What is causing this to have barriers? Right, so the source of the barrier, well, there's kind of, in some sense, two problems. One is that it costs energy to break it apart. So this cleavage, this is what's called a heterolytic bond breaking, where the electrons are not shared evenly, cost energy. Right? And another thing is that solvating ions, right, in the solvent may cost energy as well. Right? Well, we should put a question mark here because it may depend on the solvent. So if we wanted to optimize this reaction, make it go faster, we have two physical things that we can deal with, right? What we think about a catalyst is what is at that point, and what chemical structure is at that high energy point, and what can we do to bring it down in energy? Right? And there's two things that there are two kind of physical sources of bringing that in. Okay. So unfortunately for this reaction, right? So there's two ways that we can do this, right? One way is to make the leaving group, the Br, fall off more easily. Right? And there's not really an easy way to do that in this reaction. If this were an OH, for instance, we started with isopropyl alcohol, we could bring an acid in and protonate that OH to make isopropyl OH2 plus. And you lose water. But you can't do that with bromine. Bromine can only accept one bond. Right? So it's kind of hard to make this, say, like an HBr leaving to form hydrobromic acid. But that might be an option. Okay. So one thing that we could do is maybe acidify this. What happens when we acidify? So one option could be acidify. Right. But the question, of course, is that you have an H plus floating around somewhere. Where the hell does that H plus go here, right? Not immediately clear. Well, maybe it could go on the OH, right? But we also have OH. Right? And of course, if we bring H plus in here, we're just going to make H2O. And now we just remove the base. So the reaction goes slower. Right? So that doesn't work. But if our starting material was isopropyl alcohol instead, sorry, that's a really bad CH3 group. That's also really bad. Here we go. If we had this material, we could do an acid-base reaction. Get a positive charge there. And then you readily form an ion, or cation here, because that OH just leaves. The OH2 just leaves if it makes water. Okay. And then maybe the Br could come in and react. And then you would form CH3CBr, isopropyl bromide. But notice what I've done. I've just gone backwards. Okay, so what I've done is I've catalyzed the reverse reaction. Right, so acid's no good. All right, so I can't really use, at least in this simple example, I really can't use a chemical material to really catalyze this process. You may ask, okay, well, if H is going to make things worse, I could put OH in, right? But OH is a part of the stoichiometry. Not really quite it. pH is, of course, but the pH won't matter here. The idea here is that, well, at the very least, what we could say is that as the pH falls, this reaction becomes harder and harder. Right, so one conclusion that we could say is that at the very least, reaction becomes slower at low pH. Okay, so that doesn't really help us at all. Okay, that's, again, but this is, I'm just kind of going through the analysis here, right? What can we do to stabilize the transition state? Now, this does stabilize a transition state, but it only stabilizes it for the reverse case. Right? It makes it easier to go backwards. So that's not what we want. Right? What that would do would, right? We want to lower the forward rate. Right, so we have to think of something else that's going to promote the formation of pluses and minuses. So the trick is to think a little bit more abstractly, in the sense that what are other things that are floating around in this material that are also participating kind of indirectly. Remember, this is not done neatly. This is done in a solvent. Right? We have water in here, for instance. There's some solvent. And so there's a solvent choice in here. And so what we would want to choose is a solvent that promotes the formation of pluses and minuses, right? We would need a protic polar solvent. Right? So actually, what all we have to do, right, is to pick a solvent where pluses and minuses are more favorable to hang out, more stabilized. Right? So for instance, the solvent for the catalyzed process, right, the solvent choice could be H2O, right? Or acetic acid. Right? What are some other polar salts? To a lesser extent, CH3CN. Right? Polar solvents. Right? Meanwhile, if I run this in chloroform or hexanes or dimethyl ether, right? These are non-polar, non-protic solvents. The reaction is going to be higher in energy, right? So here, the solvent is participating in the intermediate. The solvent provides the stabilization to the ions. So in an SN1 reaction, the solvent acts as a catalyst. Right? Solvent is what provides the energetic stability to the ions in the intermediate. Right? Again, that doesn't mean it's participating in the reaction. Right? It's not that the liquid, the solvent molecules are getting there and plucking things out. That's not what it means. What it means is that the environment that it provides some energetic stabilization, because ions are more willing to form in a polar and protic and a polarizable solvent. Right? A non-polar solvent ions don't like. So this is still a form of catalysis. Even though it's not necessarily participating in the reaction, it's providing a catalytic environment. The choice of environment is important, chemical environment. So that's an example of catalysis. Typically, we don't often think of solvents as catalysts. typically we think of solvents as something that you optimize, right? You go ask Dr. Trillo, right? He'll say, I go try my reaction in all the solvents and I pick the one that takes the most mild conditions and gives me the biggest yield and doesn't take a week. But those are just kinetic questions, right? He wants something that's stable, something that reacts quickly and reacts at mild conditions, meaning you don't have to push it that hard. And that just means the solvent that he chooses is acting as a catalyst. Let's look at something more direct. Right? What about there are catalysts that involve themselves chemically directly with the high energy intervenes as well. In fact, most catalysts do. So it can also be an active process. Okay, 15 minutes. And it can also actively participate in the intermediate or transition state. Right? You guys on the homework are looking at a process that takes advantage of those catalysts. Right? If you've looked at the current homework so far, we're looking at a system where you either form a right-handed product or a left-handed product, and the catalyst you choose has a preference over the right-handed path or the left-handed path. The catalyst brings both down, both energies down. The catalyst makes both of them feasible, but it actually stabilizes one more than the other. So that catalyst participates actively in the reaction. So let's look at a more classic example of a catalytic reaction. Right? And I want to look at a place where catalysts are used on a daily basis in industry. Is the hydrogenation of double bonds. This is ethylene with H2 to form ethane. This reaction is done at massive scales. Ethylene is used for all sorts of things, but this is a classic example. And this requires a catalyst. So typically this catalyst industrially is a surface of a metal such as platinum or iridium are really common examples. But all right, and we call this heterogeneous catalysis. Where the idea is that you have a metal surface. Got a surface here. So this is our platinum surface. Right, and we flow ethane gas. We flow gas over this surface. And our ethylene over this surface. And there are little, it chemisorbs, it absorbs to the surface. You form these little CH2 bonds at the middle. And you form some hydrogen atoms from the H2 here. And then everything recombines to form CH3. Let me color code this. Right. We looked at that for the Haber-Bosch reaction. This is called heterogeneous because it's multiple phases, right? You have gas, substrate, and solid catalyst. Right. The vast majority of industrial catalysis is done heterogeneous. In fact, everyone who owns a car has a catalyst in the car. A catalytic converter is a heterogeneous catalytic reactor that takes O2 and unreacted gasoline to finish the job, if you will. Catalytic converter finishes the combustion job the engine didn't do, amongst others. So that's a heterogeneous reactor. But you can also do this homogeneously. Right, which is in the same solution, same phase. Right. Homogeneously, say with liquids and solvents. And this is often done in the lab, right? Small scale, this is typically done small scale. And using complexes of metal atoms with organic ligands. Right? These are called organometallic catalysts. And I used to be an organometallic chemist. And I have quite a bit of trauma associated. I want to look at an example of a homogeneous catalytic mechanism. And this is a much more classic example of a catalyst. This is a material that in some sense sits in your molecules and attaches itself to your reactants, does something to them to generate the products, and then reconstructs itself to begin. So it goes through a cycle. Right? So the catalyst goes through multiple chemical stages, but it always ends back at the original position it was left off of. So it can start over. So typically these are done in cycles, catalytic cycles. Right? And most catalysts, this is how catalysts don't affect the stoichiometry, because you bring in 1 mole of catalyst at the beginning and you're left with 1 mole at the end. Now in the middle, you might lose some catalyst, it forms something else. It reacts with your products, your reactants. The point is that at the end of your stoichiometry in your reaction, the catalyst is back and ready to go for round 2. These are catalytic cycles. And so let's look at a catalytic cycle for this reaction. Right, this is a really common kind of basic catalytic cycle. Right. So this is our catalyst here. Right, it's a rhodium chloride. Typically, L is a phosphorus with 3 benzene rings attached to it. That's a really classic phosphine catalyst for this reaction. It's what's called triphenylphosphine. You can buy it at Aldrich. It's called PPH3. Typically, that's the one that we use, but there are other types of catalysts, and people make their own depending on what they want to do. Right, so you've got this catalyst. It's a salt. It's a solid, a powder. You put it in your solution, right, and you form liquid or aqueous. Well, let's just say solvated aqueous in your solvent, right? So what happens is you take your salt and it loses a ligand and replaces with a solvent, right? So you solvate the system. You now have a homogeneous catalyst because now you have this solid material solvated. All right, so let's look at how this reaction works. The first thing that does is H2 comes in. It does what's called an oxidative addition, which is where the metal inserts between the bond of the H2 bond and break it, right? So now you have what are called 2 hydride bonds. I'll color them. So if this is red, right, you form now 2 H2s, right? Just like I had before on the surface, the H2 falls apart and the H's stick to the metals, right? It does the same thing here. In oxidative addition, rhodium is really, this is an electron poor metal, and actually this is actually very favorable. So this happens rapidly. Write that here, that rapid. And then what happens now is the CH2, the ethane, comes in and displaces the solvent and attaches to the rhodium through what's called coordination. So it's not a chemical bond, effectively, it's sort of like a half bond. What we should really draw here is that you have these little p orbitals here on the carbons, and the rhodium atom is connected to them. Right, so that's called pi coordination. All right, so it's like holding on to so it's got these two hydrogens up here floating around, and the rhodium is holding on to the ethylene like a barbell. Okay? The ethylene hasn't reacted at all. It hasn't formed any single bonds. It's just holding on to the ethyl from its pi orbitals, p electrons. Okay? So it's just like holding on temporarily. And then what happens is one of these H's attacks the methyl group, or one of the CH2s, and then you form a single bond between the rhodium and the other carbon. Right, so this attacks here. Right, and we form a bond. Well, it does it the other way, but you get the idea. So now we have one of the hydrogens here. Right, and we have now a formal single bond between the carbon and the rhodium. So this is H insertion. Okay, and now what the metal can do? The rhodium carbon bond isn't very strong. All right, this is not a particularly strong bond. That's a terrible color. And the reason why is that carbon is not particularly electron weak or electron poor, and the rhodium is electron poor. It doesn't really, there's not enough electron really. You lock it in place. And so the opposite of an oxidative addition happens, right? The opposite of an oxidative addition is reductive. Opposite of addition is elimination. Elimination. So it's the opposite. And now what happens is that instead of oxidizing H2 to form two rhodium bonds, you're reducing the carbon rhodium bond and the rhodium hydrogen bond to form ethane. So we do another insertion step effectively. And it kicks off ethane. And this is our product. And then as you can see, once I lose that H and that CH2CH3, I've gone back to my original rhodium catalyst. The process can start again. Right, so this is what's called a catalytic cycle. Right, and this catalyst, as you can see, is doing real chemistry. I mean, it has multiple chemical steps. There's two exothermic steps and a coordination step, which is also mildly exothermic as well. This is doing real chemistry. You might even need to calculate it. I think it's also changing the oxidation state of the rhodium, though I have to do the math. I think it is. Almost certainly. The rhodium oxidation state is changing as well. There's real chemistry happening. But as you can see, that whole chemistry is, over the course of the reaction, net zero. It does a bunch of things and then it undoes it. And then we just start over it. Okay, so this process can happen ad infinitum. Right? It just keeps going and keeps going and keeps going. Right, so what are some observations that we can make about this? And then I'll finish up here. Right, well, the first observation, let's think about this for a second. Well, as I said, the rhodium undergoes real chemistry. Every cycle. And of course, the question is how many cycles can this do? Well, I don't know. It depends. Some catalysts will eventually decompose, right? You can imagine that there's some side reaction that could happen with the rhodium where it gets stuck. It can't break apart. Maybe it's reacting with something else in the mixture. I think there's some ways to kill. There are certainly side reactions that could kill this catalyst. But there's nothing that I can see here. In fact, based on this theory, it would go on forever and ever. But that's generally not true. Catalysts have what's called a turnover number. Which is the average number of cycles the catalyst can do before breaking down, before decomposing? Right, that's a great question, right? So, think about it like this. If you have a millimole of ethylene that you want to make into ethane, how much catalyst do you need to put in there to get 100% conversion? Well, that depends on how many ethylene molecules the catalyst can associate with and react to before it falls apart. And that's the turnover. Typically, turnover numbers are huge. Typical is greater than 10 to the 6 turnovers. Millions of turnovers. Right? And so what that means is that catalyst, because one catalytic molecule can react a million plus, maybe 10 million ethylene molecules before destroying itself, then the concentration of the catalyst you need is very small. Right? Effectively, if you wanted it to be 100%, the theoretical maximum catalyst you would need to add is a millionth of the concentration. So typically, catalysts are performed at very sub-stoichiometric amounts. Sub-stoichiometric amounts. In fact, you would say that a good catalyst, right? You would probably want something like 0.1% relative concentration of the catalyst to the substrate. Right? So if you've got 100 milligrams, typically if you got like 100 milligrams of some reactant, you're doing pretty good if all you need for your catalyst is the equivalent of half a milligram, right? So the same milligrams. You have to deal with moles here, not plates. But that's the thing about catalysts is really powerful, is because they regenerated themselves and theoretically they can go through millions and millions of cycles before they die. That you only have to put a small amount in. If you're really lucky and if you have a really great catalyst, you can put in a tiny amount and then you can recover it and then use it for another reaction. A really great example of a material that does this is the Grubbs catalyst, the ruthenium Grubbs catalyst, which if you ever talked to Dr. Sun or Tara Ibrahim, the PhD student upstairs, he does Grubbs metathesis catalysis on polymers. And he could take his ruthenium catalyst that he uses to make those polymers and extract it and recycle it and start over and use it fresh. It has an insane turnover, which is why Grubbs won. One of the reasons why Grubbs won the Nobel Prize for that catalyst is because it's so effective and so robust. It works for everything. It catalyzes any reaction you would want that it's supposed to catalyze, and it's recoverable, which is really great because the last thing you want is ruthenium all in your mixture. That's really nasty stuff. So I don't think Tarek recovers his catalyst because sometimes it's just easier to throw it away and start over new. But theoretically, if you had a really, really rare catalyst that was a good, well-designed catalyst, you could recover it from your mixture and use it later. That's a good catalyst. Okay, so now you should start thinking, how is it going to affect the kinetics? Because if you have a million reactant molecules for every catalyst, you can imagine that if you have enough reactants, they wait in line for the catalyst. And the catalyst can only react one mole equivalent at a time. And there's a million molecules per one catalyst. You can imagine those molecules are like forming a queue. They're waiting in line for the cashier. The cashier is our catalyst, right? And so even though this speeds the reaction up, in fact, this reaction basically doesn't go without the catalyst. It has to be there. The kinetics aren't as fast as you may think, because the catalyst can only react so fast and with so many molecules at a time. And so there might be a situation where we have so many reactants and our catalyst just isn't efficient enough that we get a deadlock. That what we're doing is we add more molecules, they're just waiting longer and longer to interact with the catalyst. And so the rate doesn't increase as much as you would think. This is a huge deal in biochemistry. We'll talk about when we get back from Thanksgiving, we'll talk about the classic biological catalyst, the enzyme. All an enzyme is a catalyst. And we'll talk about the rate kinetics of catalysts or enzymes. how bringing molecules, different concentrations of molecules affect their activity. So we'll think about activity versus concentration. And think about the limits of those things. And we're going to be from that, we're going to learn about inhibition and agonism and all of these terms you might have heard for your antidepressant drugs. We'll talk about all of those next month. Otherwise, have a lovely holiday, guys. I'm mostly done with your homework. I'll have them back.